Deriving the formula to calculate the power output of a hydropower plant using Bernoulli's equation, which is based on the principle of energy conservation, which is also the first law of thermodynamics. This is a simple model of a hydroelectric dam. We're going to choose 2 points, one on the surface of the reservoir and one on the surface of the river. And at point 1, which is on top of the reservoir or on the surface of the reservoir, we have a velocity equal to 0 because velocity is just the change of height over change of time. And the reservoir's cross-section is much larger than the channel's cross-section. Another way to look at this is just to say that the flow rate equals to the velocity times the cross-section. Solving for velocity, we get flow rate over the cross-section, and the cross-section is really large, so we get a velocity of almost equal to 0. The pressure at point 1 is also equal to the atmospheric pressure because at point 1 the water is exposed to the atmosphere. At point 2, the velocity is also equal to 0 because the river's cross-section is much larger than the channel's cross-section. And at point 2, we also have a atmospheric pressure because at point 2, the water is exposed to the atmosphere. Writing down the Bernoulli's equation gives us P1, which is pressure at point 1, plus rho V1 squared over 2 plus rho GH1 equals to P2 plus rho V2 squared over 2 plus rho GH2. The two pressures are the same, so we just can cancel them out. They're equal to the atmospheric pressure. The both velocities are equal to 0, so we also can cancel them out. From the two sides of the equation, we are left with rho GH1 equals to rho GH2. If we move the rho GH2 to the left side, we are left with this term, rho G times H1 minus H2. And H1 minus H2 is just the head or the height difference between point 1 and point 2. But this clearly is not equal to 0 because none of these values are equal to 0. So the first law of thermodynamics states that energy is always conserved. In this case, the potential energy has been converted into electric energy and friction due to head loss, which is a technical term for energy converted to friction in a fluid system. If we write this down over here with its units, we get that rho is just kilogram over meter cubed, G is just meter over second squared, and H is just meters. And this is just newtons, kilogram meter per second squared. This is meters, and this is meter cubed. We're left with this, which is newton meter over meter cubed. This is equal to joules, so we get joules over meters cubed. If you multiply this by water flow, we are left with this or this, because multiplying this by water flow cancels out both meter cubes from this equation, and we are left with kilogram meters per second, which is just newtons times meters over second, or newton meters over second. This is just equal to joules, so we're left with joules over second, which is equal to watts. We also have to take into consideration the friction, or the energy that's been converted to friction. And we're going to say that eta, the small Greek letter eta, equals to the efficiency of the generator, which is the amount of energy converted into electricity. Finally, the power output equals to eta, or the efficiency, times the water density rho, times gravity, acceleration due to gravity G, times H, which is the height difference, times Q, which is the water flow. Note that hydropower plants have a power output capacity, which cannot be exceeded. When the theoretical power output exceeds the capacity, usually due to a big height difference, the flow rate of the water is decreased to match the two values and save water. So when the height is really big and it causes the power output to exceed, the theoretical one to exceed the normal one, the capacity, Q is decreased to match the capacity of the power plant. And these are the sources that I used to make this video. Thank you for listening.